Okay, we'll talk very briefly about quantum computing today. Quantum computing. Very interesting because just like the quantum states, there are multiple quantum states in an atomic state. Wow, this sounds like physics, huh? That physics allows changes in electron spin polarization. And guess what that means? By knowing the spin polarization on different electrons, holy cow, we're talking about electron level data. I want to repeat that, electron level data. We can vastly increase the quantity of information, the availability and size of microprocessors. I mean, minimal sizes now, because you're dealing with electrons, not transistors, electrons, being able to interpret electrons. So what they have is they call it valleytronics. Now that that's been increasing over the last couple years. And what it means is it uses the electrical charge of electrons as a means for storing information. Wow. And the quantum number of an electron to encode the data. Incredible stuff here. So what happens with quantum computing? You get a plot of electrons relative to their momentum or spin that provides the information that you're trying to transmit. Wow. It's not just an on and an off. It's a potential position. So it's quantum computing. And what they did was they established that this ability to control that polarization and to then control that electron density as well, we're talking atom level computing. And that gives us silicon-based quantum information processing. Absolutely incredible stuff. But so what? So we use atoms, so we use electrons, so we use spin rates, so we use momentum. So what? Well, here's the so what. By using those things, we can now make processors, or very, very shortly, they'll be able to make processors that run so much faster, carry so much data, not 100 times, not 1,000 times, thousands of times smaller, thousands of times faster, thousands of times more efficient. Incredible stuff. So if you start talking about artificial intelligence, then just imagine quantum computing can give that artificial intelligence life. It started about 75 years ago. Let's see, becoming as important. That was the first nuclear device about 75 years ago. And about the 1990s, people started talking about programmable, functional quantum computers. And now that people say that, well, we're only 15 to 20 years away. And when the quantum computers come out, they'll make the laptop that you have today seem about as sophisticated as a lump of coal. It will be cheaper and faster, and literally it will be like today you're riding a horse and tomorrow you got in a fighter jet. Millions of times, I want to say that word again, millions of times more powerful than today's fastest supercomputers, able to solve problems like dead accurate weather prediction, modeling protein molecules. Imagine that. And here's the really fun part. With all of that power, we talked last week about the ability to encrypt and decrypt. You remember we talked about secure communications? Well, holy guys, indestructible encryption. Indestructible, and able to break the hardest encryptions that we have today, just like they're not encrypted at all. Millions of times faster, millions of times more effective and more efficient. Just about every major country in the world, from the UK, China, Russia, Australia, Netherlands, US, everybody, funding research on quantum computers. Even though a lot of the research is open-ended and shared, some of it's very secretive. There are some startups, partially funded by Amazon and the CIA, that are already making hybrid machines that take a traditional silicon computer and they sort of trying to mesh it up with a quantum computer, or at least part of it quantum, but they really do not have any standards yet because nobody has it to work perfectly yet. They did have and have made a qubit, which means a quantum bit, and it's a 4 potential, because when you're dealing with quantum stuff, it's potential, 4 potential zeros or 4 potential things. For example, there's a possibility of split, merge, separate, coalesce, join, all of those different ones, all at the same time. And so when you think about those capabilities, a single qubit or quantum bit is the simplest unit of quantum information. Simplest unit of quantum information. How do they work? Well, they do not have one state. They do not have 2 states. It's like a 3-dimensional device. So there's no such thing as exactly 0 or exactly 1. It's kind of mostly 0, kind of mostly 1, somewhat something else, or somewhat something else. And all of those done at the same time. Usually these are running off of how light would be reflected, really. Photon changes. Remember we talked about earlier about just actually dealing in the momentum or the spin of an atom. Okay? So what they've actually done now, they do have a qubit that works, but they have not yet generated a quantum computer. And because it's like the first country that gets one, they'll be like winning the arms race. Okay? So do some fun. Do some research, have some fun, go look up quantum computing and look at the absolute millions, literally millions of times faster. Going to be an incredible breakthrough. Have fun.